Morning, guys. So today we're going to be starting into our second big unit in Physics 11. This is going to be a unit on what's called dynamics or forces. You may have encountered forces in some junior science classes here. Forces are simple pushes and pulls. We're going to see how forces are actually needed to cause acceleration, and we're going to use acceleration as our connection back into our kinematics. So even though this first little bit here, we're going to dive straight into forces here, you're going to find towards the end of this chapter, we might start seeing some of those kinematic equations come back again. There's a really nice sort of connection between these two chapters. So if you can just start a fresh new page in your notebooks here, let's deal with here Unit 2. We'll be on dynamics. Dynamics has to do with sort of the moving parts of the system, the workings of the system, the how it behaves, right? That's why they use the term dynamics here. And our main word here, like I introduced here, we'll say it's forces. So forces, by definition, is just a push or a pull. Seeing as push and pull sort of have direction, so you can imply their forces are vectors. From our earlier chapter, we knew vectors have magnitude and direction. So you can lift objects upwards, you can push things downwards, you can push things to the left, right, up, down, right? The units that we're going to use are actually units newtons, in honor of Isaac Newton, and we're going to use a capital N for that there. The N is actually a derived unit here. We're going to see a formula later on that N is actually related to a kilogram meter per second squared. So either you write N, which is nice and simple, but we know sort of intrinsically here, it's based on some of the other SI units here. It's like a mass. We know something measured in meter per second squared is an acceleration. That's just one way of measuring this. In terms of forces here, you can separate them into two categories. First category of forces here, we can call them contact forces. As the name suggests here, if it is a contact force, it requires touch. It requires things to be physically, in contact for it to actually act. So for example, we're going to deal with a lot of applied forces. In our section here, applied can be, I decide to pull this string, or I decide to push this object, right? I need to physically be touching the object, or I can't move it at a distance. Another sample contact force here is like friction. Friction always opposes motion. Friction is sort of, it's the resistance to surfaces sliding against each other, but as it suggests, the surfaces have to be in contact for them to actually slide. Let's contrast these contact forces. Let's contrast them with, of course, you can call them non-contact forces. More often, though, we call these ones here action at a distance forces. So they can act at a distance, they can act sort of remotely, they can act even if things are actually not physically touching. So non-contact forces can be examples like gravity, right? Even though when you're standing there, right, we would imagine, well, I'm in contact with the earth. But let's say you jump, gravity still acts on you whether you're touching the earth or not. Electric forces or magnetic forces. Magnetism is a non-contact force. Again, same thing for your fridge magnets. Of course, your fridge magnets can be in contact touching the fridge itself, or if you hold the magnet just a little bit off the surface, you're going to still feel that tug, still feel that attraction towards the refrigerator. Of course, there's many more forces up to this as well. For this first section here, I'm actually going to take a quick detour, and I'm going to introduce to you what are called fundamental forces. This part here is just for understanding's sake here. There's not much I can test you on directly for this, but essentially the idea is when you start looking at these forces like applied force or forces along strings or along pulleys and sliding forces and friction forces, all these forces are actually a combination of some fundamental forces. Since our universe was created, we actually only had a couple fundamental forces. So I just want to start here in our study here. Most physicists would disagree with me in this first case here. So if you continue on to physics here, we're actually going to say gravity is actually not a force as well. But just for simplicity, for our understanding for physics 11, physics 12, gravity, it's a fundamental force. Since our universe was created, it constantly is an attraction between things that have mass. And in fact, the things that have more mass would tend to have more gravitational attraction. Again, I mentioned if you go on to physics here, you're going to see gravity in itself is actually not a force. Gravity is actually some strange warping of space-time. Right? We'll get into a little bit of this strangeness when we get into the relativity section, but just treat it for simplicity right now. Let's think of it as a force. Think of gravity as a pull that always pulls objects that have mass close together. we really don't really encounter this until we start talking about like planetary size objects. Let's say this is the Earth. Let's call this one here M1. And let's say we had the moon. This one here is going to be M2. So these ones here definitely have mass. Gravity is a force that is an attractive force. The Earth is going to pull on the moon. We're going to call it an Fg, so F for force. We're going to always be adding these subscripts, these lower letters, just to indicate to me sort of which force I'm talking about. So the Earth and the moon are attracted by gravitational pull. They actually pull together. Were it not for the moon's actual velocity, the Earth would just steadily absorb the moon. The moon would just head straight towards it. But in fact, when our solar system was created, there was all this tangential velocity. It was actually moving, where the moon was actually in a spiral motion. It's actually because of this force here. Imagine the moon is just trying to go straight upwards here, but because there's a centripetal force here, there's a force towards the center because of gravity. It ends up dragging the moon here a little bit inwards. So now the moon is over here, and the moon still gets pulled off. It's still trying to go off, just sort of straight off in that direction, but it's always because of this gravitational pull that actually keeps the moon in orbit. Right? We're going to learn Newton's laws in a couple classes. Newton's third law says forces always exist in equal and opposite pairs. This is a little bit weird to think about. So far, it's fine. Okay, the Earth attracts the moon, I get it. But what we're going to see is forces are always in pairs. So just like the Earth pulls on the moon with a force of gravity, the moon is also pulling equally hard on the Earth, also that same force of gravity. But how come I see the moon is in orbit around the Earth and not the Earth in orbit around the moon? In fact, in this case here, obviously, it's because the moon is a lot lighter, right? A smaller object here can experience much more acceleration than something that's a larger object. We'll get into that with Newton's laws. In fact, both of them are actually orbiting each other, but they're orbiting a point. We're going to call that point here the center of mass. So if I just sort of look at the system here and I say, what's the center point that they both orbit around? The moon is in orbit around the center of mass. Because the Earth is so much more massive, this center of mass here lies really close to the Earth's center. The Earth itself is also revolving. It's actually orbiting around the center of mass, but we really don't see that revolution at all because it's so much buried deep in the center of the Earth. But that nonetheless here, forces are still equal and opposite. However hard the Earth pulls on the moon pulls on the Earth. You can make that note to yourself here. It's because the moon has less mass. Less mass is easier to accelerate. Although we will see in Newton's laws here, forces are equal and opposite. Forces are equal and opposite. So there are some concepts that we just introducing here, and we'll dive into a little more detail later on. In fact, we're going to see a formula later on. Gravitational pull actually acts between any masses. If you're sitting beside your partner, you also have a gravitational pull that's constantly pulling you towards your partner. But how come I don't feel it? Well, because our masses are so tiny, the gravitational constant is actually so tiny, it's like 10 to the negative 11, that we actually don't feel it until we actually look at planetary size masses. So we'll do that in a later lesson here, but one important note is gravitational pull is always an attractive force. There is no repulsion because of gravity. All right, so let's skip over to the other three fundamental forces. These ones here physicists do agree on. Early on in our universe here, we had what's called an electromagnetic force. You can see sort of from the name of it here, it's sort of part electricity and part magnetic. And we actually did a lot of studies for electrical studies is like positive and negative charges. Magnetic, we deal with north and south poles. In Physics 12, we're going to see how we can play around with magnetic fields, play around with magnets, and actually use magnets to actually cause electric fields or vice versa. Run a current here to actually generate magnetic fields here. These are sort of two sides of the same coin. In this case here, our electromagnetic field here, these are forces between charges, if we're looking at the electricity side of the coin, or poles. So north and south pole. We know just in terms of the sign. So if I have opposites here, if I have a positive charge and a negative charge here, we have this intuitive notion: opposites attract. Right? Positive pulls negative. Forces are equal and opposite. What if I have like charges? What if I have a positive and a positive like this? If I have a like charge, similar charges, similar, they actually repel. So unlike gravity, which is always an attractive force, the similar things will repel. In exactly the same way for poles, if I had, let's say, a north pole of a magnet and I have a south pole of a magnet here, those are opposites, so they're going to be an attractive force here. If I put two, let's say, north poles together here, they're going to repel away from each other. If you ever put sort of two wrong side magnets together, you would have feel this repulsion here. You can probably, like because the magnets are not super strong, you can probably force it to get close together, but given an option, they want to actually push away from each other. We're going to see later on that the force actually depends on the distance as well. When the charges are close together, they actually experience a lot of force. Let's say I have a positive, let's move this negative out here. Because this negative here is actually farther away from the positive than earlier, the force is actually going to be weaker. Even though the sign is still going to be the same, I'm still positive, negative, I'm still opposite, I'm still attractive force. It's just the amount of attraction is going to be weaker. So the amount actually depends on the separation distance, how far away things are from each other. The third force here, we really don't have a really good feel of this one here because this one here acts on atomic scale. So we're going to call this one here the strong nuclear force because this one is the stronger of the two. And the strong nuclear force here, the most important sort of interpretation that it's doing here is it ends up holding our nuclei together. So if you ever thought about this way here, what are our nuclei made up of? So let's just take a look into a little bit of the chemistry here. Let's take a lithium atom as an example. Lithium is element number 3. So what's happening here is inside our core, we have 3 protons. Each of those protons here have a positive charge. We just said if I have similar charges, they actually hate each other. And especially when they're squeezed into so close together, the force of repulsion is just ridiculously strong. Well, how come my atom can actually stay together then? If you imagine there is an imaginary set of hands here, I know the protons are hating each other, they're trying to get away from each other here, but it's actually this strong nuclear force that's actually gripping these ones here. It's like holding two opposite pole magnets together, and we're sort of keeping it together there. The strong nuclear force here, part of it is because of the neutrons as well. The neutrons act like little spacing molecules. For lithium, it actually has 4 neutrons here. Even if I can separate the protons ever so slightly here, it would actually increase the ability for the strong nuclear force to hold our nuclei together in a very, very dense core for our atoms. So for our strong nuclear force here, it's important, although because we typically don't have experiments on the atomic scale, we really don't have much of a feel for this. In a similar fashion here, since we had the strong nuclear force, we also have what's called the weak nuclear force. This one here is not as strong. And one of the implications for this weak nuclear force, this one here is responsible for a bunch of radioactive decays. So for example, we can say, let's say beta decay here, you'll learn this in your chemistry courses. Let's say one of these neutrons actually converts itself into becoming a new proton. It ends up decaying away. It ends up shooting off a beta particle, which is basically an electron. And for that process there, it deals with the interplay of the weak nuclear force. So these are our foundational forces. And somehow by combining all these forces, we're going to get to understand the forces that we're interested in this chapter. So I just want to make this note here, why we took this quick detour in the fundamental forces, all the other forces that we're going to deal with. Today I'm going to introduce to you like a normal force or gravitational force here. All these other forces, we're actually going to do it in this order here. Now gravity itself can be itself a fundamental force, but definitely when we talk about like a normal force today or even a friction force in upcoming classes here, all these other forces that we're used to, like tension force, things like that, are a combination of these fundamental forces. So since our universe was created, because these are the main foundational forces, these ones there can combine together to give a whole bunch of other variety for all other forces. Just to give you a feel for this sort of normal force here, imagine you're just standing on the ground. We're going to start analyzing this in terms of free body diagrams later on. Basically, I want to ask the question, well, what are the forces that act on you as you stand here? Well, we know, because I am a mass and the Earth has a mass here, we know that there's a force of gravity that acts on me. There's an Fg. We're going to call that a weight in a second here. If that were the only force, I would fall straight through the ground. How come I'm actually able to stand on the ground? Well, I know the ground is actually supporting me. This time the ground here is actually just straight across here. We're going to call this one here a normal force. A normal force, we're using the terminology Fn. A normal force, the normal just means it's perpendicular. It's not like it's a regular force. perpendicular. That's called the normal force. Essentially, the ground is supporting you against gravity. And how hard is the normal force pushing? It has to counteract gravity. It has to get rid of gravity trying to pull you downwards so it can actually support you. Well, this looking at our list of fundamental forces, normal force, this perpendicular force here, isn't a force in itself. In fact, it's actually, well, the atoms that make up the floor here. I know the strong nuclear force are keeping all the atoms together. There's an electrostatic force attracting between positive and negative charges all over the place here. It's the combination of those electromagnetic forces, electrostatic forces here that are allowing the surface to actually stay as a whole to actually eventually provide for you this normal force that supports you going upwards. So just to show you, all the forces are some combination of those fundamental forces. Nicely, we're going to lay out this chapter here. When we do our calculations, we always do it in a certain ordering. So I can just introduce you that ordering here. The first force we're going to deal with is actually just the force of gravity. Again, for simplicity, we're calling it one of our fundamental forces here. Even if it's just this weird bending of space-time, it's a combination of the other three fundamentals. That's fine. For force of gravity here, we're going to say Fg. And in fact, this force of gravity here is what we know to be weight. So here we get back to our age-old question here. What's the difference between mass and weight? You may have encountered this question here back in earlier science classes. One difference is definitely the units. When we measure mass, our SI unit was kilograms, right? Mass actually describes for you, I think of it as the amount of material, the amount of matter, the amount of stuff that makes you up. It's the matter, it's the material. Weight, however, is actually another name for force of gravity. Weight is actually the force gravity pulls on you. And because weight is actually a force, this one here is actually getting measured in newtons. Sure, these ones here are related to each other. Usually if I have more substance to me, gravity will pull harder. There's more mass to hold on to. So definitely there's a proportional relationship, but these two things are actually different. In everyday life, sometimes you ask, well, like, how much do I weigh? What you're actually asking is actually the mass. You're actually not interested in the force. Your scales are actually measuring how many newtons. It just does the conversion right away, and that's why you can just read right from the scale, oh, I weigh 50 kilograms or 60 kilograms or whatnot. I'm actually asking mass. So in science, we want to be really, really precise with this one here. Mass, again, if you take a look at an object, let's say I have a solid, I assume it's actually made out of many, many particles here. Well, there's a lot of material that makes up this bulk sample here. The amount of material is the mass. So let's do an example here. Let's say here I am standing on the Earth's surface. Maybe my mass is 50 kilograms. There's 50 kilograms worth of material making up my body. Again, it's a little bit strange because, well, the atoms themselves are mostly empty space. All the material is sort of in the core, but nonetheless, that sort of makes up my body. I'm 50 kilograms. That's my mass. Let's teleport me out into outer space or maybe close to the moon or whatnot. If I pretend that the teleportation here, I didn't lose an arm or a leg during the transport here, I'm still made out of the same body. My mass is still going to stay the same. It's still going to be 50 kilograms. However, when I'm actually interested in weight in science here, I'm actually interested in, well, what planet are you on? How much gravitational pull does it actually experience here? In this case here, when I'm on the Earth's surface, we're actually going to revisit that number. We had said the acceleration due to gravity is 9.8. We'll actually come back in a later lesson to actually calculate this 9.8. But basically, based on the mass of the Earth and based on the radius of the Earth, how far away I'm standing from the Earth's surface, I actually know it's going to accelerate my mass of 50 kilograms. Each 50 kilograms is accelerated by 9.8. We're actually going to come to our first formula to find the weight. The Fg, force of gravity, is actually mg. That's going to be a formula on your formula sheet here to find your actual weight, which is your force of gravity. This one here is actually measured in newtons. It's proportional to the mass. If there's more to grab onto, you're going to definitely weigh more. The g here is actually another name for that acceleration due to gravity. If we assume we're on the Earth's surface, this acceleration due to gravity, we can assume right away it's that 9.8 meter per second squared. And we're going to avoid that whole notion of, oh, shouldn't it be negative 9.8? Remember, in kinematics, negative just gave you a direction. We're actually going to start off in this lesson here drawing pictures, drawing arrows, really pointing which way things are. as long as I point the arrow, let's say towards the center of the Earth, I don't need to say negative 9.8. I can just calculate whatever the size is and then just multiply by 9.8. It's that positive number that gravity actually pulls down on you. So let's just try it while I have it there. So what is so my mass is 50 kilograms. What's my weight if I'm on the Earth? So my weight would actually equal to the 50 kilograms multiplied by the 9.8 meter per second squared. This gives you here 490. If you just multiply the units, here's where I can see kilogram meter per second squared. It's a little bit tedious having to always write that. We just define the new unit, newtons. So my weight, I would actually say, is 490. And the weight actually describes how hard is the Earth pulling down on you. I may have 50 kilograms worth of material, but my weight is actually 490. Based on the planet's mass, based on the planet's radius, it's pulling down on me 490. Now back to my analogy, I didn't teleport in space. My mass has not changed. I still have my whole body. I didn't lose a limb along the way. However, when I'm in outer space here, maybe I'm on the moon, right? The moon is sometimes, well, it's only a fraction, maybe 5 times, 6 times, maybe even more than that, smaller than the Earth. So the force of attraction is actually weaker. So what would happen here, usually we throw around a number, the acceleration due to gravity is about 1/6 the acceleration due to gravity on the Earth. So what's going to happen here is instead of multiplying 9.8, we're going to multiply a number that's smaller, and therefore my weight would be, I'm not going to calculate here, but my weight would be something like, oh, I'm only 100 newtons or 80 newtons, something like that. Then I get my really lame joke here. What's the best way to lose weight? Well, why not just go to a planet that has less mass, right? Or go to a planet that's a little bit larger. We know the force also depends on the separation distance as well, right? So there's our first formula. Pretty much all you need is the mass. Definitely this formula is telling you mass and force of gravity are proportional. When one gets bigger, the other gets bigger, right? They're directly related, if you want the terminology here, right? So that's why they're so commonly confused when I say, oh, how much do you weigh? Well, the more mass, the more gravity pulls down you. If you have less mass, the less gravity pulls down you. But there we go. We get our formula. Fg is equal to mg. All right. I'm going to introduce you one more force in this lesson here, and that is what's called the normal force, like we talked about earlier. Normal force, I'm going to use F subscript n, right? And again, I mentioned here the n, it stands for normal. It doesn't mean like normal in the sense of, oh, it's regular, it's routine, whatnot. That n there actually means it's perpendicular to the surface. So in your math classes, if you draw a normal actually it's a perpendicular line. For starters, we're going to have the surface that's just straight across. So perpendicular to that surface would just be straight upwards, right? So normal definitely refers to this perpendicular bit here. The other part that isn't immediately obvious here is I do have to be on a surface. If I was even like a smidgen, like if I took a jump off the ground is not supporting me anymore. I will only have a normal force if I'm physically touching the Earth's surface. And it's a perpendicular force. The trouble with normal force, let's just stand back on the ground again. The trouble with normal force here is there really is no formula for this. So, unfortunately for us, there is no formula. You won't see it on your formula sheet. There's no formula because the ground supplies what it needs to, right? In that situation. So now that doesn't help. Okay, let's look at a few examples. We had just calculated our weight. So my mass of 50 kilograms. I know the acceleration is 9.8. We'll calculate that number later on. My weight is 490. So I know that on my body, because I'm on the Earth's surface, Fg is pulling me downwards 490 newtons. Right? I don't need to worry about negative because I know just from the picture here, I know that's downwards. Again, like we said earlier, if this were the only force that's acting on you, you would fall straight through the Earth's surface. Well, I know that doesn't happen. I know then the ground has to be supporting me. I know the ground is actually pushing against gravity. How hard does this normal force, this force here perpendicular to the surface have to be? Well, if gravity is pulling you 490, the normal force would actually have to be 490. It has to be opposite gravity so that your net force cancels out. So that 490 cancels out 490, so there is no overall push or pull on you. So in this situation, definitely the Fn is equal to 490. No formula for that. It just supplied what it needed to support you. Now, what if I did a similar scenario here? I know this is my mass, right? I know the force of gravity on me is, so Fg is equal to 490. let's say what I do is I decide to put on a really heavy backpack. And let's say this backpack in itself, I was only 50 kilograms. Let's say I put on a 10 kilogram backpack. Well, now in total, I'm actually like a 60 kilogram object. That means gravity in total is actually pushing even harder on you. You can just actually calculate what's the force of gravity on the backpack. Again, we can just say mg. If I have 10 times 9.8, that adds for me an extra 98 newtons just on the pack itself. The arrow is a little bit smaller. This arrow here is an extra 98 newtons. So that in total, the Earth is actually pulling down on you some 500, almost 600 newtons worth. Just because you put on your backpack doesn't mean you suddenly fall through the ground. So therefore, what does the normal force have to support to actually fight against? Again, because we sort of know the answer, we know the guy is just going to stand there. The normal force now needs to fight against both your masses, the 490, as well as the backpack's force of gravity as well. You're not going to get this formula anywhere, but from the picture, it says Fn has to support the Fg for your person plus the Fg for the backpack. And if you look at those numbers there, you could say, well, my person was 490 newtons, the backpack added an additional 98. In total, how much pull is acting on you? 490 plus 98 gives you here 588. And therefore, in total, we have 588 pulling you downwards. So therefore, my Fn has to increase to 588. The Fn has to support, let's write this in words here, the ground in this second situation, the ground supports your mass and the backpack. Right? Because again, I'm assuming when you put on the backpack, you don't suddenly start sliding and falling through the ground. Right? Let's do one other situation here. So let's say here you are standing here, right? I know I have a mass of 490 newtons, so I put down the backpack. And now this time what's happening is there's a bird that comes up behind you. Now what you want to know about this bird here is external to the system. It has nothing to do with you. But what this bird does is it comes up behind your shoulders and it actually starts trying to lift you. It then supplies a force. Let's supply a force of, let's say, 100 newtons. Right? So the bird is sort of perched on your shoulders and is trying to lift you up 100. First question you want to ask yourself is the bird pulling hard enough to actually lift you off the ground? We're going to think in this chapter in terms of tug-of-wars here. Well, there's a tug-of-war here that's 490 going downwards. I'm only pulling 100 upwards. I'm definitely not going to counter gravity. I don't pull enough to actually lift you off the ground. However, the bird does do something though. Because the bird is supporting 100 newtons, if my normal force continued being, in the first situation, the normal force was 490. If the ground continued supplying 490, the bird says, sweet, the ground is supporting you and I just need the 100 and I now lift you off the ground. Nope. This time the ground gets lazy. The ground says, all right, I know the bird isn't pulling hard enough. But since I'm kind of lazy here, since you're supporting me 100 newtons anyways, why not me just push upwards 390 newtons so that together with what the bird is doing, it then cancels out the forces. It then makes you just stand there. So not only do we have no formula for this Fn here, it just pulls what it needs to. Again, you're not going to get this formula anywhere. In this case here, our Fg, our total 490, is being supported by the force from the bird, our 100 newtons, and we're seeing what does the normal force change to so that it cancels out. So if gravity is 490, that's pointing in the downward direction. These two forces are helping each other, so both of them are upwards. That's why they're being added. The bird is supporting 100. What is the ground doing as a difference? Well, the ground would then have to be, let's just put it as Fn for now. The ground would actually have to supply 390 newtons. Right? The ground will actually support you a little bit less. This is actually given a name, not only normal force. The normal force is sometimes called the apparent weight. This is how much you think you feel. And you notice I used to be 490, but because the bird is perched up on your shoulder and because it supports you 100, you end up feeling lighter. We feel lighter, and that's because our apparent weight is actually less. Right? The bird is not pulling hard enough to lift you off the ground, but definitely the ground says, thanks, bird, I don't have to push as hard anymore. Right? You start seeing we are labeling these arrows, right? All forces are vectors, right? We label the direction, gravity goes downwards and this one goes upwards here. Realistically, the picture is a little more complicated because gravity doesn't act on all my body all at once, right? my head is a little bit farther from the Earth's surface, my legs are a little bit closer to the surface, my parts of my body may be a little bit more dense, right? More matter, more muscle mass, maybe. Parts of my body may be a little bit less dense or whatever. Realistically speaking, gravity acts on your body differently for your entire body. Just for simplicity, however, what we're going to do, sort of like we did with that Earth-Moon analogy here, we're going to assume that instead of actually having a body, actually having some shape to you, we're going to imagine that we squeeze you into one point. That point there is just going to be called the center of mass. So if you tell me that you're 50 kilograms, instead of 50 kilograms is sort of divvied up, here's the head and here's the body, here's the legs, I'm going to imagine that 50 kilograms is just in a singular point. And therefore, I don't need to start worrying about, well, how does gravity act differently for your foot as acting on your head here? I can just say, well, gravity pulls 490 on the center mass here. So what I'm alluding to here is usually in the first part of these problems here, what we're trying to do is what's called a free body diagram. And essentially what you're going to do is you're going to label all forces acting on this center of mass. In Physics 12, you're going to come back and you're going to worry about something called torque. That's going to actually need to worry about, well, how is the mass actually divvied up? At least in Physics 11, we'll just deal with a single point. And basically all we're going to do is we're going to have a dot that represents your entire body and your entire mass. And I'm going to just label the arrows just to indicate to you what forces, what pushes and pulls there are. Just a caution as you start learning into this here, for free body diagrams, people tend to draw too many arrows. Only draw an arrow if you can really identify there's a push or pull. So on your worksheet, there's going to give you a few different scenarios here. Let's say I just have a box on the surface here. On your worksheet, it might say static. Static means things are at rest. Things have canceled out. So when you put this mass here on the slope, it just sits there. I'm going to imagine that this entire mass here got squeezed into a singular point, and I'm going to ask you, well, what are the forces that act on this diagram? Well, there's gravity, right? That's what's keeping everything, is pulling things towards the center of the Earth. Gravity actually doesn't care you're on a slant. We'll come back to analyze this picture in more detail in a later lesson. But gravity pulls straight downwards. What other forces act on this object? Well, in this case here, I know the object is just going to sit there. That means gravity doesn't win. If gravity were the only force, this mass here would just fall directly through the ground. So we do have a surface. This time our surface is actually ramped at an angle. If we do perpendicular to the surface, that's going to be our normal force. That's the one we didn't have a formula for. That's the one that's trying to support you against gravity. There is one more force, however. Well, gravity would typically make this thing here slide down the ramp. What's possible that's on the ramp that's actually keeping it up the ramp? Well, in this case here, we're going to see there's actually a friction force, an FF. We'll deal with that more in tomorrow's lesson here. But when you have a friction force here, it always opposes motion. Those are the only arrows that actually act on this mass here. Why I say people tend to draw too many arrows. Let's say back to my kinematic study here. Let's do a football study where we have sort of, here's the ball and we sort of launch it. Yes, while it may be true, when the ball was just sitting there, you had to apply a force just to get it going. Remember, this applied force is a contact force. The instant that the ball actually leaves your foot, you can no longer influence it. So it's not like through the entire path, you're actually finding the ball and you're pushing it along. The ball was initially given some force. So this is some initial applied force. But what I want to emphasize to you is the second that the ball is no longer touching your foot, you can't touch it anymore. And therefore, were it not for the starting velocity, from here on out, it's just gravity that's acting. Because gravity does pull on it over the entire course of the motion. You're not constantly behind it. You're not constantly needing to actually push it along just to keep it going. It already had that starting velocity, and it's just that same x velocity that just continues onwards. So the one big idea from that section there is you don't need forces for motion. You just need forces for acceleration. So on your worksheet, you'll get some practice drawing some of these free body diagrams. Use the dot for the center of mass, and basically you're labeling the arrows. The size of the arrow tells you how big these forces are, and the direction will tell you the heading. All right, so keep practicing through there. If you have any questions, just let me know. Thanks, guys.